Hey, hello everyone. Welcome to Physics Teacher. So in this live session, I'm going to be going over the unit on dynamics in the grade 12 physics course, as my class has a test on that tomorrow. So I'm going to go over some multiple choice questions and then we'll go over some sample problems. So let's start with the first one. So the first one here we have a car is traveling north when it enters a curve. So it's initially going north. Let's make this north. It enters a curve, it maintains a constant speed and leaves the curve traveling east. So it ends up traveling east in this direction. What is the direction of the car's acceleration? So the motion sort of looks like this. Curving, your acceleration is always directed towards the center of that curve. So that's one hint that it's going to be southeast. Okay, another way you can do it is you can look at final velocity minus initial velocity. So there's final velocity. Your negative initial velocity is down this way. And so if you add those, you get, again, southeast. Okay, so our answer is going to be A. Next one. This is one of my favorite ones. I love this one. So 24 kilogram traffic light is suspended from the midpoint of a cable suspended between two poles. So it already sounds pretty complicated, but let's keep reading. Make sure we focus on every word here. So the angle between the cable and the pole is 80 degrees at both poles. The net force acting on the traffic light has a value of what? This is a multiple choice question, and sometimes I'll see students working on this for 5, 10, 15 minutes, and I have to catch them and tell them it shouldn't take this long. Okay, because it shouldn't, right? This information you do not need. The only information you need is asking for the net force and the fact that it's suspended. So if it's just held there, what's the net force? 0. Okay, no calculations required. All right, moving on. So an elevator accelerates downwards. What's the relationship between the gravitational force and tension? Okay, so let's just draw this here. Here we have our elevator. It's going to have a cable, some force of tension. It's going to have gravity downwards. Now, those will be the same if the elevator is either at rest or moving with a constant velocity, but in this case, it is accelerating, and it's accelerating downward. If it's going to accelerate downwards, that downwards force needs to be greater because the net force shows you the direction of acceleration. So that means gravity needs to be greater than tension. Not greater than or equal to. It's not equal to. It's not less than. Here it is. It's greater than. So gravity greater than tension. Any questions so far? Hi, Keaton. All right, then. Moving on. For objects traveling with uniform circular motion, the centrifugal force, that's our fictitious force, right, they experience is, so centripetal force is always radially inwards. Okay, that's the real force that causes circular motion. Centrifugal force is the fictitious force you feel when you're inside of this circular non-inertial frame of reference, and it is in the opposite direction. So it's radially outwards. Okay, so this is true. But don't get too excited. Let's just check the other ones. Is apparently present in the non-inertial frame of reference. It certainly feels like it is, doesn't it? So that's also true. Increases with speed. Yep, doesn't actually exist. That's true. So our answer is E, all of the above. All right. I know people don't usually like this, but proportionalities. Planet X has a mass 8 times that of Earth, and acceleration due to gravity is 19.6. You might realize that that is exactly 2 times normal, 2 times 9.8. So an acceleration due to gravity twice that of Earth. What is the radius of planet X? So we looked at an equation for G, right? From universal gravitation. We can set gravity equal to gravity, right? Because it's the same thing, right? Where this is a universal gravitation, GMM, over r squared, and that's going to equal mg. So your equation for G then is just G times the mass of the planet over the radius of the planet squared. All right then. Well, if G is going to be twice that, and m is going to be, I'm going to stick a little 8 in here, 8 times the normal. For this equation to still be true, it looks like we should have a 4 down here. But be careful not to choose this one, right? Because 4 squared is 16. So what you actually want is a 2 there, because it's r squared. It's inversely proportional to the radius squared, right? So 2 squared gives us 4, and 8 over 4 is 2. So 2 times. Any questions with that one? There are lots of ways you can solve that one. It's fun to think of proportionalities. Well, my students don't think so, but maybe some do. All right, so let's try some actual questions. We're going to start with some circular motion questions. I got 2 examples for circular motion. The first one is in a vertical plane. So here we have some object whirled around in a vertical circle on a 1 meter long string. So that's telling us what the radius is, 1 meter long. So we got mass and radius with a constant speed of, so we got speed, 8 meters per second. Okay. What is the minimum speed of the object so that it still maintains that circular path? So if you want to know the minimum speed, you want to look at where that object is right at the very top of its motion. Because it's either going to just continue along that path, or it's going to fall short. Okay, so let's look at our forces that are acting on it. So it looks like we've got, this is a string, so we've got tension acting down, and we have gravity acting down. So choose your positive direction. Always choose the direction that's in the direction of acceleration. So we'll make down positive, center seeking, and we'll write the sum of all forces equals, or contributing to centripetal force equals mass times centripetal acceleration. So all our forces here, we've got tension plus gravity is equal to, now we have different equations for acceleration, but since we know speed, we're going to write it as v squared over r. Now here's the thing you have to remember, right? As speed, so let me write this, as speed approaches that, don't know how to write here, as speed approaches that minimum speed, right, tension is approaching 0. And because the instant tension is 0, you're falling, right? That rope is no longer taut. You're not continuing that circle anymore. Okay, so as this goes to 0, this becomes V minimum. So now we have Fg. We know the equation for that. That's mg. And that's going to equal m V min squared over r. And we can cancel the mass and figure out what that minimum speed is, right? Multiply by r, take the square root, and we get the square root of gr. So let's put in some numbers here. G, 9.81 meters per second squared, and r in this question is 1.0 meters. Okay. Calculator now. So the square root of, well, 9.81. 3.1. There we go. I hope that proportionalities, oh, they could be on the test. They could be. I certainly went over it for a reason. Okay, so next one. I love this question. Here we have a 50 gram, don't worry about the dash. Not 50 grams, a 0.5 gram insect rests on a compact disc. That's a CD. A CD is like a DVD. Feel old now. At a distance of 4 centimeters from the center. Okay, so we have this disc, and it sits on it somewhere over here at a radius of 4 centimeters. So it's going around in a circle of radius 4 centimeters. The disc rate of rotation can vary between 3.5 hertz to 8 hertz. Okay, so what's the minimum value of the coefficient of static friction that would prevent the insect from slipping at the slowest rotation rate? So this is the one we care about right there. That's the slowest rotation rate. And we want to know the minimum value for static friction. Okay, well, here's our insect. Let's go ahead and draw the insect. There we go. Free body diagram of an insect. Now from this bird's eye view picture, we're looking down at the insect. So gravity is into the screen and normal is out of the screen. They're both perpendicular to the direction of centripetal force. So what's keeping the insect there? What's preventing the insect from flying off? That's going to be static friction. Yeah, we're not going to look at air resistance. That's going to be negligible. The only thing holding that insect there is its grip, right? So that's static friction. We'll write that to the side. If he's right here, static friction is perfectly left. And that we will label as our positive direction, because we want to choose our positive direction to be the same as acceleration. And that's the only force. Right? So then we just go ahead and apply Newton's second law. Sum of all forces contributing to centripetal force is mass times centripetal acceleration. The only force we have is static friction. And I'm going to use the equation for acceleration that involves frequency, because that's what we're given now. So that's 4 pi squared r times frequency squared. Okay, now it doesn't ask us for the minimum value of static friction. It asks for the minimum value of the coefficient of static friction. So our equation for static friction, let me go over to the side here, is the coefficient times the normal force. Now, just like I said before, the normal force is going into the page. Oh, sorry, no, coming out of the page. Gravity is going into the page. Normal force is coming out of the page. And that insect is not accelerating in that direction. Right? It's not taking off or anything. So we can set normal force equal to gravity then. So we have static friction is equal to mu s times the normal force, which is equal to gravity, which is mg. Yeah, that's fine. Do you think I can? Sure. Right? Especially if you're working ahead, you can definitely get a 90. Where are we? So static friction, let's just substitute that. Mg equals m times 4 pi squared r frequency squared. So masses are going to cancel. So we didn't even really need to care about that mass of the insect. Okay, and we can just divide by g to figure out what that coefficient is. So we have 4 pi squared. R is 4 centimeters, but put this into SI units, so 0.04 meters times our frequency, which is 3.5 hertz. Don't forget to square it. I get a lot of students that forget squares. and then we divide all of that by our 9.81 meters per second squared. Okay. So now we need our calculator. 4 times pi squared 0.04. It's 3.5 squared over 9.81. 1.97, but we want only 2 significant digits, so 2.0. There's our coefficient. You'll be okay, Julian. You'll be okay. Not too bad. I'm sure it's worse than... I was going to say worse than you think. No, I'm sure you think it's worse than it is. All right, one more question. And I'm also going to recommend you go do another question. But let's look at this one. So here we got a pulley question. I think this was similar to the one you had in your quiz, but let's go over it. So we have all this set up here, including friction. Oh, hold on. There we go. Including friction, and we need to figure out the acceleration. Okay, so this block is accelerating up the incline. So let's make that our positive x direction. And then our pulley rotates our coordinate system. So here's going to be our positive x direction. Okay, let's write all the forces here. So we've got tension. And if it's sliding up that ramp, kinetic friction is in the opposite direction to motion. So we've got kinetic friction here. Gravity, straight down. This one's the smaller mass, so I'm going to label this as small mg. This is just how I like to do it. You can label it as m1 or m2, but I like to label the small one as lowercase m and the big one is uppercase m. Okay. And we got the normal force perpendicular to that surface it's in contact with. Okay, always put normal force perpendicular to the surface and gravity straight down. Okay. All right, now that we've done that, oh, we got one more force here. We got tension. All right, so now that we've done that, we need to look at our coordinate systems and see, are there any vectors not aligned with them, and write components. So that's only gravity. So let's write components for gravity. Looks like this. Those should be perpendicular because we've got an x and a y. Always include your arrows. Okay. So if this is 30 degrees, that is also what this angle here is going to be. So our y component, we have mg cos 30, or I'll just call it theta. It's called 30 degrees theta. And mg sine 30 in our x direction. Okay. We've done a lot of drawing. Let's apply Newton's second law. So Newton's second law says the sum of all forces in x, we're going to apply it along our x component, is mass times acceleration. Now it's times acceleration in x, but because I've labeled our positive x direction to be the same direction as acceleration, that's just going to equal acceleration. And let's look at all of our vectors in x. Now this is tension, and this is tension. And they're opposite directions. They're internal forces. If we're looking at, actually, we are looking at both masses. So hold on. Oh no. Okay, let me erase it here. Back to the pen. So we're looking at both masses. So it's m plus m times a. I'll write that out better here. M plus m times a. So to find acceleration, we're sort of looking at both masses moving together. Okay, you can look at them separately and solve a system of equations, but I find this to be a lot faster and easier once you get used to it. So when you do that, tension is internal forces because they're pulling back on each other. And so it would be one minus the other. So it's going to cancel. We have this big mg, that's positive, so mg. And then we're minusing this component of gravity right here. So minus little mg sine theta. And then we're minusing kinetic friction. So what's the value of kinetic friction? Let's write our equation. It's mu k Fn. And what does Fn balance with? Fn balances perfectly with this component of gravity. It's not accelerating in this direction or in this direction. It's not doing either of that. It's not flying off the ramp. So those forces will balance. So we can rewrite this as minus, because it's in our negative direction, mu k. And then our normal force, which is equal to mg cos theta. So it's one long, ugly equation. But that's it. That's all the physics. So if you're just solving for acceleration, divide both sides of your equation by the sum of the masses. Okay. And then you have the value for acceleration. Okay, we've got lots of questions here. Oh no, those are not questions, just comments. All right. So at this point, you're just going to plug in the values. This is the last question I have here. So all the values are given. I'm not going to plug them in and let you watch me use my calculator. I'm sure you can do that. But another question I wanted to tell my students to go over, if they haven't, is adding vectors in 2 dimensions, right? Similar to that force table we used in class. And I made a video for that lab. And in that video, I go over an example for how to do it. Okay. So go check that out. And if you have any last minute questions, I'll stay for a minute before I go. Otherwise, I'll see my students tomorrow. And if anyone else is doing a test, good luck. It'll be okay. Okay, no questions. You're welcome. All right. Have a good night, everyone.